So now in this regression equation part 1 video, we're going to start looking specifically at the regression equation and trying to determine eventually how to come up with the regression equation. As we've been doing all semester in this particular course is we're going to be using samples. So we're going to look at data from a specific sample to come up with an equation based on that sample. Eventually, we'll look at, does that sample provide evidence to allow us to make predictions about the population? To get started, we're going to explore the idea. You've worked with scatter plots hopefully before. We're going to look at scatter plots. Scatter plots are great ways to visualize our data, especially when we have two observations, the independent variable, the x variable, and the y variable, the dependent variable. So each pair of observations is plotted as a point on a graph. So here's an example of a set of data. If you go to your textbook and you read the chapter in textbook, they're going to use this example throughout. So this is a set of cars. We have 11 cars. They're called Orions, some fake car company. And here we have the age of the car and the price of the car. So our first car is 5 years old and was $8,500. Okay. And so on, and so on. The second car is 4 years old and is $10,300. So we're trying to determine, in this sample, what kind of relationship does age and price have? Can we use age as a predictor for price and that kind of information? So to do that, we build a scatter plot. So take each data, 5, 8 of 5, 4, 103, and we plot it on a graph. So here you can see, that we do have this kind of linear relationship happening. What we're looking for in our scatter plots is the data. So for your work in StatCrunch, one of the things that you can do when you have a data set is you can pull it into StatCrunch, go to graphs, and click scatter plot, and you will get a visual scatter plot. Use the technology as much as you can as you're going through this work in chapter 14. So here's a set of data that appears we can have, we can fit a linear equation where the points are scattered about it. But for example, suppose I had some crazy graph that looked more like, hold on. Suppose you had a graph that looked like that. Notice we are only doing linear regression. There is a whole other field of polynomial regression where you can fit a polynomial to a graph like that. Think of a parabola, but we're not doing that here. So if you get a diagram like this one and ask, ooh, does it appear you can fit a linear equation? Well, that answer would clearly be no. You would not be able to use a data set that had a scatter plot that looked like this, and you would not be able to represent that one with a linear equation. So there are some things you really need to be careful of. There are also graphs that start to appear, or that start to maybe appear okay, but then jump somewhere else. That would be another one where it would be very difficult perhaps to get a linear equation around it. So just these are some things you're going to look at, because you could put it one this way, you could put one, I lost it because it could be more like this. So some things you want to look at, and there are some examples in the homework that you'll go through. Okay, but to really look at this a little deeper, what I want to do is use a much smaller data set. We're going to use this very, very, very simple data set right here. 3 points, okay? We have the 0.13 We have the 0.21 and we have the 0.31. So I'm going to go ahead and I'm just going to draw a random line. Not random. It is random because I'm not using any mathematics to actually come up with this particular equation right this second. And now I'm just going to draw a linear equation around those particular data points. And the reason for that is I want to go over some notation for a second. So this equation, let's take a look at the data points. The data points themselves are your xi's, yi's. So when you see a notation with a little I on it, that represents the raw data, the actual data points. So x sub 1 would be 1, x sub 2 would be 2, and x sub 3 would be 3. Y sub 1 is 3, and so on and so on. So I want to make a distinction for a second between these different y values. Again, so here's a point, and this is an x, comma, y. That's a data value. So if you, for this particular data set, when we use 3 for x, we got 5 for y. But when we build a regression equation to fit the data, our regression equation, is not going to give us a 5 when we plug in a 3. It's going to give us this value right here. And this value is our y hat. So the y hat is the y value you get when you plug x into the regression equation line, okay? Where y sub I is the actual raw data value. Now, the difference between these is called the error, and it's represented by a small case e. The error is simply the y value from the data minus the value you get when you plug x into the regression line. So it's y minus y sub hat. All right? So just to identify some of the different y values that we're going to work with. But notice, I could build different regression lines that look like they fit those 3 data points. So here's 2 perfect examples. A line could be built that looks like it fits the regression line that is -1 plus 2x. Then a line could be built that also looks like it fits those 3 points that is 1 plus x. The question becomes, which of those 2 lines is the better fit? Whoops, sorry about that. To do that, we use what we call our least squares criterion. The least squares criterion is that the line that best fits a set of data is the one having the smallest possible sum of squared errors. Okay? So let's take a look at that. What we're going to do is take each of our 3x values and we're going to plug it into our regression line to find out what our y hat values are. So let's take a look. All right? Regression line A was -1 plus 2x. X and y represent our raw data. But if you take 1 and you plug it in for x, you get 2 minus 1. You get a y hat of 1. If you take 2 and plug it in for x, you get a value of 3, and so on. The error is the difference between the actual y value and the predicted y value using the regression equation. So the error, 3 minus 1 is 2, 1 minus 3, -2, 5 minus 5 is 0. The error squared is simply taking that error and squaring it, which gives us 4, 4, 0, and 8. If we do the same thing for that line B, we get a different set of values for y hat because we had a different equation. Our y values are the same because that's our raw data, but because we're using a different equation, we get different y hat values. So therefore we get different errors. We square those errors, and then the sum of the errors squared for equation A was 8. The sum of the equation squared for line B is 6. And the least square is going to be line B because 6 is less than 8. So according to these two lines, if you were asked which one is the best fit is going to be line B because it has, according to the least square criterion, the least squared errors. So what I want to do is apply this least square criterion to a new set of data. So this particular data came from a professor of Arizona State calculus class. The independent variable, or X variable, is the total study time over 2 weeks, and the dependent variable is the grade the students received on their tests. So the first student studied for 10 hours over 2 weeks and got a 92. Second student studied for 15 hours and got an 81, and so on and so on. So we've got 1, 2, 3, 4, 5, 6, 7, 8 students. Here's how much they studied. Here was their test result. We have 2 possible regression lines. We're going to figure out which of these lines is the line of best fit. So to do that, first thing we need to do is go to regression line A and calculate what the y value would be for that regression line if the number of hours were plugged into. So let's take a look. Sorry, forgot to turn my email off. So how would we do that? So for y hat A, I would first take my 10 and plug it into line A. I get y minus, I get 99 minus 1.25 times 10, 99 minus 12.5, which comes out to 86.5. So I get 86.5. Then, to get my e squared, remember e itself is going to be the actual y value from the student who studied for 10 hours, which was 92, minus the predicted value if that particular regression line was used. And we're going to square that. So go on your calculators and take 92 minus 86.5, square it. So it looks like we get what? 5.5 squared, 30.25. Okay. We would do the same thing for line B. We would use that value of 10 again, but this time put it in regression line B. Which is going to give me 96 minus 10, 86. And now for error squared for B, you are going to take the 92, which was the raw data, the score the student actually received, minus the 86 and square that. So that's going to give me 6 squared, or 36. I want you to hit pause. I want you to complete this particular table and come up with the line of best fit. So here you can pause the screen again and kind of take a look at what I got. I got the summation of line A to be 120, the summation of the errors for A to be 126.31, B to be 89. So clearly B is the line of best fit. And the next video we'll look at what really